Hi everyone. This is a story about the circles activity we did the other day in class. So a reminder, we have graph paper and we've drawn circles on graph paper. And the task was to do this 5 times and then count the number of boxes that are inside of a circle. So you might say this is 4 boxes inside the circle, and also count the width of the circle. So you might say that this is 2 boxes wide. And remember, this isn't a perfectly precise measurement. It's coarse because we miss this width, we miss that width, we also miss, this area and this area and this area. It's hard to fit a circle into a perfectly square box. So the data that we took looks on the agenda. It looks right here, our class's results. So this is the data, and I cleaned out the lousy points that were flipped for a couple of people. So here's the data for the diameter and the number of boxes. Now, let's see. So if you recall, we had this reading about fitting. If you go to the last page, they talk about what to do if the relationship between the input and the output, the x and the y, isn't a straight line. And so you can kind of treat this like a pattern matching exercise. If you see this line, what does this line look like? Many people in class said it looks like a curve. So y is proportional to the square of x. So we should graph y versus x squared, or try this fit line. You remember in class that we had 3 different ways to do this, so I'm going to show you at least one of them right now. So I'm going to take all the circle data from Google Docs and copy it, and then in Logger Pro I can paste it. Here's the same data. I never want to leave the data unlabeled, so I'm going to double click and say that this is width. I'm going to call it D for diameter, and the units are boxes. In the same way, this is going to be something like area. Maybe I'll call it A, and it is also measured in boxes. So my graph is labeled and I've got this curve. So there are several ways to talk about fitting this that we used in class. One of them is to highlight it, highlight all the data, and then try a straight line, which, as we talked about in class, is horrible because it's high and then it's low and then it's high and it doesn't really predict what's going on. And look at this y-intercept, negative 68 boxes when there's no width. There's a lot of things that don't make sense about a linear fit. A curve is what we thought would work. And if you remember the handout, the curve was y and x squared. So if we go back here, we can define a function, and we could say that a times d squared plus b is our function. So d is the input variable, right? Width in boxes, we called it d for short. And a is a slope and b is an offset, because maybe we need one. So when you define that, and maybe I should have given it a better name than proportional, we can try it out. And if you try it out, it goes through the data pretty nicely. And we have a slope of 0.709 and an intercept of 5.6. Now I don't know what this intercept means, and if I don't believe in it, I can make it 0. If you do that, this slope could be better. And note, if you push the button up or down, you can find your favorite version of this. This number right here is an error. As that number gets bigger, there's more error. As the number gets smaller, the error is better. And so the error, maybe 0.72. I don't know, something like that. Yeah, that minimizes the error. So the computer plays around to figure out what the best error is. Okay, so I have A area equals 0.72 x squared plus b, and b is nothing. So that's one way of doing this analysis.